Hi, this is my Unit 8 Fix-It post. So yeah, I'm just gonna get right into it. What I'm gonna do is I'm gonna start off with the MCQ first and then cover the FAQ just like a normal test. Over here, let's see. So this is one of the questions that um, I did not get. So um, I worked this question out and I came up with the answer that the angular momentum of the ball remains constant and the rotational inertia of the ball about the axis of revolution decreases. So just like in linear motion, momentum of the system is always conserved. So I already knew that, and I was picking out between C and D. And the reason why I picked C was that, as you can see, um, the moment of inertia um, decreases, and this is because obviously we learned in class that with the diagram of someone standing on the spinner, that as you tuck yourself in, right, as you have like the less radius, you tuck yourself in, um, then the lower um, rotational inertia you're gonna have, right, which is why this is the answer. But when you're talking about it, I guess physically or mathematically, um, right here we know that um, we know that rotational inertia is some form of mr squared, right? Depending on the shape, there's going to be a constant. It'll either be 1/2 or 2/5 or 2/3, depending on the shape. But um, it doesn't even matter what it is because that's going to stay constant. The only thing that's changing is the radius, right? It's just the distance from the center. So we know that the moment of inertia is always some constant times mr squared, right? And with this, since the r is getting smaller, the rotational inertia will get smaller since they're um, proportional. So yeah, that's why this C is the answer. The momentum is conserved, it stays constant, and the rotational inertia will decrease. I guess one way to show that would be angular momentum, this thing, and then there's going to be a slide about it being conserved. Okay, I think it's right here. I think it's being a little slow. Okay, sorry about that. I think it's not working. Or okay, there we go. So they're always assuming that momentum is conserved in this case, and with that, they are finding what they need to find, either whether it be I or R or pretty much anything. So yeah, that's where I got that from. Okay, moving on to the next question. Question number 3. So this is another question that I did not have on my test. So when working this out, they give you, I guess, this image, and it's asking which of the following graphs best predicts the angular momentum of the planet, right? So when you're thinking about angular momentum, linear momentum would be p is equal to mv, right? So the equivalent of p is equal to mv. P stands for linear momentum. So angular momentum, which I don't really know symbol for. Angular. I forget. Angular momentum is just I, right? Because I kind of represents the mass, and omega, which kind of represents the velocity. It's the angular velocity, right? So I omega, right? And it's asking the graph of angular momentum from position A to position B. How does it change, right? So we know that it's I W, right? So the moment of inertia of the planet will not change, right? Because it's just going from one place to another, same shape, right? It's going to be the exact same radius, nothing's changing. So the moment of inertia stays the same, right? Now we're talking about omega, right? Omega is also going to stay the same. So we know this is constant in some way, right? Actually, one thing I forgot to point out, I is the same, but like I said about I earlier, some constant times mr squared, right? Now, when we look here, both of these, we know that when we're talking about planets, like the circular planet, it's not usually a perfect circle, right? So when it's closest to the kind of the star that it's orbiting, it's the fastest, right? But in this case, looking at the picture, they're the same distance. This is r. This is r. One is just going in the left direction or negative direction. One is going in the right direction or positive direction. So they have the exact same distance from the star, right? So when we're talking about I, it's mr squared, right? So same m, they'll have the same constants, it's the same shape. And then the radius, it's the same length, right? The only thing is this is in the negative direction and this is in the positive direction. But remember that I is mr squared, r squared. So because it doesn't not matter if it's negative or not, because it's always good. R squared is going to result in a positive number, right? So we're looking at angular momentum. Omega is going to stay the same because it's always the same distance from the center, right? We know that because we were taught that the closer it is to the object that it's orbiting, the faster it's going to go, right? But because they're equal distances, omega is just going to stay the same the entire path, and I is going to stay the same because the only thing that's changing is like the radius, direction, but it's r squared, which means it wouldn't matter. Therefore, it should be constant. It'll have an angular momentum, but it'll be constant, which is why it's between C and D since it's constant, but it has an angular momentum. So I pick C. Okay, this one. This one was pretty easy. I did not have this on my test as well. So for this one, we have a force strength with F going downwards, right? And it's asking us what at what point should you put a force of 2F to make it equilibrium so that the system doesn't have torque, right? You don't want a net torque of 0. You want a net torque of 0, right? And so when you're thinking about it, this is, I guess, 2 tick marks far out from the center, right? And you're applying a force F. So obviously to balance that out, you would want to, you're giving a force of 2F, right? So to rotate something, right? To rotate something, just like your moment of inertia, pretty much. If you're tucked in, right, the closer you are, you go faster, right? But to actually rotate something, just like this pencil right here, the closer you go, the harder it is to rotate, right? The harder it is to rotate. Versus going on the edge, it's much easier to rotate. If I were to go right here, it's much harder to turn. So because of that, we want to do something that is closer because you're taking double the force, right? So if you want to take double the force, you need to cover only half the distance because it needs to be proportional. So you're doubling the force, which means to keep it equal to the torque exerted from this, you need to do it from half the distance, right? You're doing double for one, you do half for the other, so that it's an equilibrium, it's conserved at 0. So, and you want it to be on the same side, so boom, option B right there. That was pretty easy. This one was on my test. I got it wrong. So yeah, I mean, we can just honestly just take a look at this college one. So obviously you're going to need the radius of the sphere. The question is asking about the change in angular momentum. So kind of the impulse, right, of the sphere. Now to get the impulse of the sphere, you could do torque times the change in time, right? And to get torque, you would need, or torque net, sorry, you would need force times the radius, right? The radius perpendicular to F. So you have the force, right? Given the problem, it says something about measuring the tension force. A net force is applied tangentially, blah, blah, blah. Yeah. So sorry, you don't, this is a different problem. You need a force. You need you need to know what the force is, and you need to know what the radius is to find the impulse, because you need three things. You need, or technically two. You need torque net, and you need the change in time. We have the change in time. It's 3 seconds. It's from rest to 0 seconds to 3 seconds, right? So the problem is asking, but we need torque net. And to get torque net, you need the force and you need the radius. So three things. We have one. So we need to find the force and we need to find the radius, right? So radius and the average net force. This is kind of irrelevant. I guessed, but yeah, that will get you torque. Or yeah, the force and the radius will get you torque, which will get you the impulse, since you multiply it by time, or change in time. So that's why I picked A and D. Uniform ladder. Okay, so this one was also on my test. I also got it wrong. I got all MCQs wrong. The only points I got first from FRQs for some reason. But yeah, I completely guessed, but I understand the question now. So we need to think about the pretty much is asking for the torque, right? We need the torque. Now the forces, when we think about this, are obviously gravity, which is just mg, right? And then we're talking about what does the torque do to the weight of the ladder about its base, right? So you would have to do something with cosine, because you're trying to get, this was just the adjacent side, right? It's the x direction. So you want the cosine component of, you want the horizontal component of this, which is this. So you do L cosine theta, right? So you can automatically rule out the sines completely. The only thing is, I'm not sure why it's over 2. Just kind of, hold on. Let's see, angle letter. There we go. So, yeah. Sorry, I'm just trying to figure out. Okay, so I don't know why it's over 2. But yeah, I know that has to do with MGL cosine theta. That's what I got out of it. Okay, this one I also got wrong. It's asking what is the magnitude of the wheel's final angular momentum, right? So we know that the angular momentum at rest was 0, obviously, because there's no angular velocity. Yeah, angular speed or velocity. So now it's asking for your final. So asking for the final will be the same thing as the final minus 0, which is the impulse, right? And earlier we know that finding the impulse would just be torque net times the time, right? And so looking at this, I had the question earlier. Boom. Yeah. So you need we know the torque, or sorry, we know the force, right? Because it says the student records the tension, right? So we know the force. Now, what else do we need to find to get the impulse? We need the time, and we need the radius, right? Because we do F times R to get the torque net times time to get the impulse, right? So yeah, I think that's it for that question. Yeah, and it says the student records the time. Sorry, that's what I was verifying. So you have the force and you have the time. So all you need is the radius. So yes, you have enough. You just need to measure the radius. So that's that MCQ. So there's just FRQs left now. Okay, cool. Okay, so for this, this one I did not get on my test. I had the Ladybug question. That's it. I had one FRQ. So let's talk about it. So it says in a clear and coherent paragraph. Obviously, I didn't write a paragraph. This is just like my preparation. In a clear, coherent paragraph, length response. Explain why this athlete's angular speed increases from figure 1 to figure 2, but decrease from figure 2 to figure 3. This is really simple. Noticing the figure, the moment of inertia right here is greater than right here. Because again, this is tucked in. Just like how in class you demonstrated with someone standing on the little spinny thingy, he spun around, he put his arms out, and it was slower, but he tucked his arms in, it was faster. Just like how ice skaters do it. You gave us the same example in class, where ice skaters, they kind of tuck it themselves in so they can spin faster and look cool. And so this is what this guy's doing. He's tucking himself in, so he has a lower moment of inertia, and so that way he has a higher angular speed, which is what makes him go faster. So it says explain why the athlete's angular speed increases from figure 1 to figure 2, figure 2 to figure 3. So it increases from figure 1 to figure 2 because same like the law of conservation. It's not a law, sorry. Conservation of momentum. So the same thing can be applied to angular momentum from linear momentum. Momentum of the system is always conserved, right? And when you're going from figure 1 to figure 2, right? Let's see. Let's do this. So angular momentum, right? The moment of inertia is going down. So for it to be conserved, the angular speed has to go up, right? So that's how I know from figure 1 to figure 2 that it increases, right? So yeah. Now from figure 2 to figure 3, it decreases because let's look. Same thing as this, right? It's gonna have very similar moments of inertia. Maybe it's like a little off because this is straight, this is a little angled, but this is extremely tucked in. This is not. So the moment of inertia is increasing, right? We're still same thing, conservation of momentum. So now moment of inertia, is increasing. So the angular speed for the angular momentum to be conserved has to decrease, right? Which is why it would decrease from 2 to 3. So I know this is a clear paragraph, but I would just go on and talk about conservation of momentum. Moment of inertia either goes up or down, so the opposite has to happen to angular speed, right? Now it's saying in part B, is the rotational kinetic energy of the athlete in figure 2 greater than, less than, or equal to the rotational kinetic energy in figure 1? So we just talked about angular speed, right? And we connected linear motion to angular motion, I guess. So for kinetic energy for linear motion, right? It's just 1/2 mv squared, right? Now for angular motion, it would be 1/2. So the equivalent of mass in I guess angular world would be I, and for V, it would be omega. So 1/2 omega squared. That is kinetic energy rotational. ROT. Right. So let's talk about it, right? We said from figure 1 to figure 2, the I will go down, right? Because you're tucking yourself in, right? You're tucking in, so the I goes down. And for it to be conserved, 1/2 won't change. So omega has to change, right? So omega would have to change. The angular speed will have to increase, right? So yeah. And instead of conservation of momentum, I guess you could apply conservation of energy. And okay, so one thing I just realized is that when omega goes up, I still going down, right? So you think, oh, it's equal, but think about it, right? For momentum, we were thinking about it from a momentum perspective. It was just IW, right? So I was thinking of momentum. So the same amount that I decreases, the omega will increase, right? So the same thing with kinetic energy. The moment of inertia will decrease, so omega will increase, but omega is being squared, so it will say I decreases by double, then omega will increase by 4 times because it's 2 squared, which is why the rotational kinetic energy for figure 2 is greater than that of figure 1, because the change in W is greater, right? So that's why, because omega is being squared, right? They're both moment of inertia and omega are changing the same amount, right? But omega is being squared when you're talking about kinetic energy, which means that it would cause kinetic energy to increase more. Does that make sense? So yeah, that's that FRQ. I didn't have it. So this one I did have on my test. So let's talk about it. We have. Okay, cool. Actually, I'm gonna do this. It'll be much easier. This is hard to look at, man. Hard to look at. So the question asks. Okay, I give you 2 ladybugs. It says, is the angular speed of the ladybug greater than, less than, or the same as the angular speed of ladybug B? So, to calculate angular speed, it's just a change in the angle, change in theta over time. They're at the same angle, right? So it's not going to change. That's why it says the same, right? But I said less than for some reason, and I included this, which is very unnecessary. It's the same because it's just changing theta over changing time. They're both changing the same amount in the same time. Might be covering more distance, but angle-wise, no. A and B are the exact same, so that's where I missed points. And then for part B, you're supposed to say that the linear speed is greater. And I said the linear speed is greater because you're covering more distance over time. A is covering more distance over time. It says, and using this formula, right? So I mentioned that in part A, the first part of part A, when I should have mentioned in the first part, the second part of part A. So I messed up there. That's where I lost a point. Now let's look at part B. It says Ladybug A begins to walk in a circular path in the direction of the disk's rotation, right? So that's what it's going to walk like this, right? Does the magnitude of the angular momentum of the disk alone, right? The disk alone increase, decrease, or stay the same? My response is it would stay the same, which is wrong. It's supposed to say that the system does not change, but the disk loses angular momentum. Why? Because the ladybug gains angular momentum, right? It's already moving like this, right? So it's gaining because you're changing the theta, right, over the same amount of time. You're changing a greater amount of theta over greater amount of theta over the same change in time. So that's why the angular momentum of the ladybug is going to increase um because omega is going to increase. So because the ladybug's momentum is increasing, the system momentum has to be conserved. So that means the disk's momentum has to decrease since the ladybug's momentum is increasing. And yeah, that's I got it completely wrong. So that's me. And then for this one, I got 2 out of the 3. It says derive an equation for I2 in terms of I1. So I did that right. I got 4/5 I1, 0.8 I1, same thing. So yeah, there's that. But I have to say that the what was the question again? Sorry. While the ladybug is walking towards the center of the disc, does it exert a torque on the disc? I said no. I just didn't know, so I just said no. But the correct answer is yes, and it says that like a torque exerted on the disc is there. They don't even give an explanation. Oh, sorry. It's because there's a torque because there's a change in the disc angular momentum, just like last part where we said the angular momentum of the disc decreased. So because of that, since there's a change, there is a net torque that's causing that, because a change in angular momentum has to be caused by a net torque. So you just say yes to that. So yeah, I got the deriving part right, but the whole is there torque? Nope. And then so last FRQ. Okay, so this question was asking about these 3 different cases, right? And there's one where the ball comes here, bounces back, while the rod is going up. There's one where the ball just hits the rod and it stays where it cuts or wherever impact occurs. And there's a third case where it sticks onto the rod. So this was not on my test, but I can tell you that the graph would look something like this. It's a little complicated, right? But when it's asking for the graph of the puck and the rod, right? So I'll tell you right now that for the puck, the angular momentum is going to be increasing from here to here because the puck is going up, right, over time. So omega is increasing, right? And so it's just gonna that's the angular momentum, right? And so there's that. And because the momentum is conserved, the moment of inertia will decrease. So yeah, it's gonna stay constant right there. And then for after the collision, it'll be just negative but the same magnitude because it's going back down. It's going in the negative way, right? And angular momentum is a vector, not a magnitude. And so it's going the opposite way, and direction matters, so that's why it's negative. Now, for the rod, it's going to be constantly 0 because it's just chilling right there. It's at rest, right? So it'll be 0 right here, and then it's going to be positive right here because it's I times omega, right? And now omega is increasing. It's there pretty much. The I is going to decrease, but it's there, so it'll just be a positive constant, right? And yeah, that's part A. Now part B would be it basically asks for a rank. I'm lucky I didn't get this up for Q because I don't understand this. I searched for the question to try to understand it, but I was pretty confused. The rank goes theta 1, theta 2, and theta 3. And that will conclude my test corrections. I did not do well.